All right, in this video we're going to look at alkylation of the alpha position. So we can attach an alkyl group to the alpha position when we react an enolate with an alkyl halide. So first we use a strong base to form the enolate, then react that with an alkyl halide, and the reaction actually proceeds via an SN2 reaction. So the enolate acts as the nucleophile, and then the halogen pops off as a leaving group. So the typical restrictions for an SN2 reaction apply to this reaction as well, and that is that the alkyl halide needs to be either methyl or primary. The enolate is not only a good nucleophile, but it's also a strong base, and so if I have a secondary or tertiary alkyl halide, then we're going to get an elimination reaction, and we're just going to form a double bond in what was the alkyl halide as opposed to getting this substitution and alkylation reaction. Now, in order to prevent an aldol reaction from competing with the desired alkylation, we want to use a strong base such as LDA or NaH so that we completely convert all of the aldehyde or ketone into the enolate. If we have a mixture of the aldehyde and the ketone with their enolates, then we're going to have the aldol reaction competing. And so we can avoid that by using a strong enough base. And as we'll see on the next slide, we have to be aware of the regioselectivity if we have unsymmetrical ketones. So in this case, I have an unsymmetrical ketone, right? I can either deprotonate this alpha carbon to make the enolate, or I can deprotonate this alpha carbon. And if we consider the stability of these, right, if we deprotonate this alpha carbon, then we have the lone pair. We can imagine the resonance structure where the lone pair becomes a double bond and the pi bond here becomes a lone pair on the oxygen. And that would give us this form of the enolate. Or if I deprotonate this alpha carbon, then I can do the same resonance structure, and this would give me this particular enolate. And this one is kinetically favored because it is less. This alpha carbon is less sterically hindered, so this enolate will form faster. But it's less stable because we know the more substituted the alkene is, the more stable it is. And so this one is favored under thermodynamic conditions. And the kinetic and thermodynamic conditions that we have here are similar to the ones that we've seen in the past. And part of it has to do with temperature. To favor the kinetic products, we would use lower temperatures. To favor the thermodynamic products, we would use higher temperatures. But in this case, room temperature would work, and for cold temperatures, we want something much less than room temperature. Right, and as is typical when we have competition between the kinetic and the thermodynamic pathways, because the kinetic pathway has a lower barrier, right, it's going to be formed faster, and it's going to be favored by lower temperatures where I can't establish an equilibrium between the two products. And so at low temperatures, even though it's less stable, the reaction is not as reversible. The thermodynamic product, the product is lower in energy, but it has a larger transition state, so this reaction happens more slowly. But if I have a high enough temperature where this reaction is going to be reversible, then I'll form an equilibrium between the two possible enolates, and this one will win out because it's more stable. So, as we've mentioned, the kinetic enolate is favored by irreversible conditions. If we do it at low temperatures, we essentially can't go backwards. And so we want to use LDA at low temperatures. The other advantage of LDA is it is fairly sterically hindered. So it's going to prefer to attack the less sterically hindered site than the one that's more sterically hindered. If I want to favor the thermodynamic enolate, and so to give me substitution on the more substituted alpha carbon, I want to use higher temperatures. So that's going to favor formation of an equilibrium where I'll get the more stable product. And then we can also favor the thermodynamic product by using a non-sterically hindered base like sodium hydride. So to do the alkylation on the less substituted carbon, I would use LDA, a sterically hindered base, and low temperatures. To get substitution and alkylation at the more substituted carbon atom, I would use a non-sterically hindered base and room temperature, but that's certainly higher than the temperatures used to get the kinetic product. Okay, in this first example, we want to predict the product and propose the mechanism for the following reaction. So I see that I'm treating this unsymmetrical ketone with a strong base and an alkyl halide, so I expect alkylation to occur, but I need to decide, is alkylation going to occur at the more substituted alpha carbon or the less substituted alpha carbon? So I'm using a non-sterically hindered base, and they don't tell me the temperature. Now, if they don't tell me the temperature, that means it's not at low temperature, which they'd have to tell me it's not as high temperature, so we can assume, if they don't tell me the temperature here, that it's at room temperature. And so I have a non-sterically hindered base at room temperature, so I'm going to have alkylation occur at the more substituted alpha carbon. So my product and now be careful. I'm forming the bond between the alpha carbon and this carbon. So I'm adding 1, 2, 3, 4 carbons. So I'm not adding an isopropyl. Right, make sure that you count your carbons and that you add the right number. All right, now if I want to draw the mechanism, the mechanism is, first I'm going to deprotonate my ketone using this strong base to form the enolate, and then the enolate is going to serve as the nucleophile in an SN2 reaction on this alkyl halide. So the first step is to deprotonate my alpha carbon. Give me that enolate. Then I'll have an SN2 reaction. Where we're going to attack and pop off the leaving group, which will give me my final product. All right, in this example, we're just asked to predict the product. Here we're using a sterically hindered base at low temperatures, and so this is going to favor the kinetic product. And so I'm going to favor alkylating the less substituted alpha carbon. So this alpha carbon is connected to 2 other carbons. This alpha carbon is connected to 3 other carbons, and so we're going to alkylate at this position. And so my product in this case is I'll attach an ethyl group there. Now the mechanism for the kinetic product is just the same as the mechanism for the thermodynamic product, so that's why I didn't require us to draw the mechanism again for this case. We would have just deprotonated this alpha carbon, and then it's going to undergo an SN2 reaction with ethyl iodide. All right, one last example. We want to know what reagents we would use to achieve the following transformation. So I can see that I have alkylated the alpha position of this ketone. The ketone is unsymmetrical. This alpha carbon is less substituted. This alpha carbon is more substituted. And obviously, I alkylated the less substituted carbon. So I want reagents that are going to favor the kinetic product. And so I want to use a sterically hindered base. I want low temperatures. And then the alkyl halide that I want to add, right, has 1, 2, 3, 4 carbons. So be sure that you have 4 carbons, and then the halogen is coming off that one. And iodine is a very good leaving group, so I'll choose to use iodine as my halogen.